All right, welcome to the Explainer. You ever wonder how a website just knows to recommend batteries right after you buy a toy? Or why grocery stores always seem to put the chips and salsa so close together? Well, the secret is all in the data, and today we're diving into a really powerful algorithm called Eclat. It's this clever and incredibly fast way of finding all those hidden connections, and we're about to see exactly how it works.
So here's what we're going to cover. First, we'll get a handle on the problem itself, why we even care about what shoppers buy together. Then, we'll look at the classic way of doing things, the a priori method, and see where it falls short. After that, it's all about Eclat, its unique vertical approach, the magic of intersection, and we'll even peek at how you'd implement it in R. Finally, we'll wrap it all up with why this algorithm is such a big deal.
Okay, let's jump right in. But, before we can really appreciate how slick Eclat is, we got to understand the fundamental problem it was built to solve, figuring out what stuff people buy at the same time.
It all boils down to this one question that every business is dying to answer. What do my customers buy together? Finding these hidden patterns in, millions of transactions is the key to everything, from how they lay out the store to the personalized ads you see online.
And there's actually a name for this whole process: market basket analysis. It's all about digging through mountains of shopping cart data to find what are called association rules. Basically, the invisible threads that connect one product to another.
Now, before Eclat came along, the big name in the game was an algorithm called a priori. It takes this very methodical, almost step-by-step approach to finding these patterns. But, yeah, that method had a pretty big catch.
So the biggest issue with a priori? It's kind of a brute force approach. To find any patterns, it has to scan the entire database over and over and over again. Think about it like this. Imagine you had to read an entire library once to find popular words. Then you had to read the whole library again to find popular two-word phrases, and so on. When you're dealing with millions of transactions, that gets incredibly slow and really expensive, fast.
And it's that exact inefficiency, that slowness, that really paved the way for a much smarter, much faster algorithm. And this is where Eclat, which by the way stands for Equivalence Class Transformation, just walks onto the scene with a completely different game plan.
Okay, this slide is where you can really see the genius behind Eclat. It's all about a fundamental shift in how you look at the data. A priori thinks horizontally. It looks at transaction number 1 and says, okay, what items are in it? Then transaction 2, and so on. Eclat completely flips that on its head. It thinks vertically. It looks at one item, say milk, and lists every single transaction where milk appeared. It's a total game changer. And this list, this vertical list of transaction IDs, is the absolute heart and soul of the Eclat algorithm. It has a special name, a TID set. So for every single item in your store, Eclat creates one of these TID sets. There's a TID set for milk, one for bread, one for eggs. Each one is just a list of transaction numbers. This simple little transformation is the entire secret to its speed.
Okay, so we have these TID sets. Now what? How does Eclat actually use them to find out which items are bought together? Well, it avoids all that slow database scanning by using a really fast, really simple math operation: intersection.
And this example just lays it out perfectly. Let's say you want to know how often beer and chips are bought together. You don't have to go back and scan the whole database again. No way. You just take the TID set for beer, transactions 1 and 2, and the TID set for chips, transactions 1, 2, and 4. Then you just find what they have in common. The intersection is transactions 1 and 2. The size of that final list, in this case 2, is what we call the support count. That's it. It's an incredibly fast way to see how popular a combo is.
Now this whole idea is super elegant, but it's not just theory, right? It translates directly into practical code. And for anyone doing data science, R is a huge tool, so let's take a look at what this actually looks like in the R programming language.
So if you look at this snippet of R code from our source material, you can actually see the core logic right there. See that little function called merge tide sets? That's it. That is the intersection step we just talked about with the beer and chips. That's the engine of the entire algorithm, right there in the code. That's where all the magic is happening.
But here's the thing, while you totally could code this yourself, and is a great way to learn, the good news is, for any real-world project, you really don't have to reinvent the wheel. Data scientists lean on powerful, optimized packages to do all the heavy lifting for them. See, in the real world, you're just going to use a pre-built, super optimized library.
In R, the R rules package is basically the industry standard for this kind of work. It has a really robust, really fast version of Eclat all ready to go, so you can run this powerful analysis on your own data with just a couple of lines of code.
All right, let's bring it all home. Why should you, as a data scientist or an analyst, really have this Eclat algorithm in your back pocket? Let's quickly go over the key advantages that make it so darn useful.
When it comes down to it, it's all about performance. By flipping the data into that vertical format, Eclat just completely avoids the slow, expensive database scans that really bog down a priori. Instead, it uses these lightning-fast intersections that happen in memory, which is way, way quicker. And this makes it an especially great choice for what we call dense data sets. You know, situations where the average shopping cart has a whole lot of items in it.
So in the end, Eclat isn't just some fast algorithm for a common problem. It's a powerful reminder that sometimes just a simple change in perspective, like going from horizontal to vertical, can lead to massive, massive improvements in efficiency. It kind of leaves us with one final thought. What valuable hidden patterns are just waiting out there to be discovered in all the data around us if we only know the right way to look?